I'll just wait for a few minutes and then start. Okay, I guess I'll recap what we learned last class. Okay, yeah, so typecasting. Um, so what we saw is like taking examples of integer I, float f, and uh, variable d with double data type, right? So all these inbuilt numbers, right? Inbuilt data types have certain bits associated with it. What I mean by that is the data type itself tries to represent the number it contains using certain number of bits. And that's decided by the standard. So usually the integer type is 32 bits, float is also 32 bits, and the double is 64 bits. The difference being that integer uses 2's complement to represent the number, and float and double use the IEEE floating point standard. All right. So printing them, we see the number. That's fine. So what happens when we try to write d equals to I? Okay. So we are setting the variable. Uh, we're setting the variable d equals to I, right? So uh, just a second. Oh yeah. Is there a question in chat? Yeah, okay. So, okay, all right. So what we're doing is setting d equals to I, where t already had some number, right? And we're setting 7 to d. Okay. So there is sort, and if you think about it, you're trying to write bits of a double. Okay. So the arrangement of the bits will be something, right? There's a sequence to the ones and zeros. And the same arrangement, uh, like, okay, so the arrangement of 7 in integer I is a certain arrangement. Okay. The same sequence of zeros and ones. If you try to just copy paste into D, it won't work because D represents floating point standard. All right. So there is an inherent conversion to represent 7 in this double uh, as a double floating point number. Okay. And this implicit casting, okay, is from integer to double. It's taken care of by the compiler. Okay. So that's one. You can do explicit casting in this way. Okay. Through this, you are more clear as to what you want to achieve. Okay. what's the intention of your code. So at least there's that. All right. But also remember, you can also do an implicit cast like this. Explicit cast makes your intention more clear. Okay. And this is a C style way of doing it. So that's what we're saying here. The other way around is converting a double to an integer. Okay. So double here D contain 8.9. So the arrangement of bits in a 64-bit fashion with a floating point representation standard, okay, had certain sequence of bits. All right. That then gets converted into an integer I, okay, where I is integer. Like it gets converted to I, which is an integer. So the conversion also takes care of converting it to an integer format, okay, to the 2's complement format to try to represent 8.9. And again, it's integer, so it can't represent 8.9, but we'll try to represent the nearest integer. Okay. Any questions so far? Okay. Then the sequence of precisions, okay, in the order in which the precision gets added, right? So that is what I mean is the hierarchy of how the implicit cast, let's say you're doing a casting from a high precision to a low precision, is in this order. Okay. So from the left side to right, it is in the higher precision order. So you have bools first, then characters, then shortened, integers, unsigned integers, long, unsigned, long, long, float, double, and then long double. Okay. I hope no doubts till now. Um, is there a question? Okay. All right. All right. So looking at the next example. Okay. So first we'll define again, similar to previous. We'll define an integer I and store 3. Then we define an integer P. Okay. So Right. Sorry. So we'll define integer I, okay, and define a pointer p, okay. So now this pointer is of data type integer, as in it points to the variable, it stores an address and points to a position in the memory which stores an integer. All right. Now that pointer is storing the address of I itself. So the p is pointing to actually number 3. Okay, right? We also define a of size 10. Okay, and then this itself becomes a array. So it's the C style array. Yeah. So right. So A is of 10, right? So I meant to say A is a C style array. So that's fine. We'll define double the variable D as 7.5, double pointer Q with the address of D, very similar to the one here with I. So P and Q are pointers. P is of data type integer, Q is of data type double. Okay, all right. And then we'll define a void pointer R. So R is a pointer, yes. But now the thing about R is the address it is storing. Okay. When you try to dereference that address, it can actually it just means that the data type is just not known. As in, you can think of it like the two ways of looking at it. Either that there is no data type. The second is it can be any data type. So it can be any data type. Why we even say that is because of typecasting. You can, like, as we'll see later on, you can try to cast it, all right, to any pointer and try to read off bits from that. Okay. So that's the other way of looking at the same thing. Okay. So if we try to set p q equals to p, so we try to set I and I, F, D and all those things. So that was fine. Okay. But what if you try to set q equals to p? So when you try to set q equal to p, like you're setting pointers, so this will throw an error. Reason being, you're trying to set a pointer which is integer, okay, to a pointer which is a double. This is as such not implicitly allowed, okay, and vice versa. So when you try to set q equals to p, like the same thing, but with an explicit cast, okay, so this is fine. You are saying that I want to represent, treat the address at p, okay, as a double pointer and then read it off by dereferencing q later on. Okay, so that's what this one means. Okay, and when you try to dereference, it tries to read the location's memory as an integer or a double, depending on which one you're printing. And by printing this dereferenced values, like doing a dereference of q and p, okay, you get the representation of the twos of let's say 7.5 in two's complement as an integer, or number 3 in a floating point representation as a floating point number. Okay, so that's what it does. When you try to convert, like, or set r equals to p or r equals to q, you're setting these pointers of some data type into void. This is absolutely okay. So here, basically, they're losing their data type of what the pointer is actually pointing to. So this implicit conversion from integer pointer to void pointer or double pointer to void pointer is allowed. Okay. Right. Then, um, obviously, you can also set your um, void pointer R and V, okay, sorry, R, by doing explicit cast. So that is also allowed. No problem there at all. Okay. And when you try to set a void pointer to a certain data type pointer, you can't do it implicitly. Again, that's not allowed. You have to do it through an implicit cast. Okay. Sorry, you can't do it through implicit cast. You have to do an explicit cast for that. Okay. And we also looked at the same thing, like trying to dereference some values and so on and so forth. So that's exactly what A of I does. So that's a side thing. Other than that, trying to set a pointer of an array. Okay, so when you define a C-style array, the variable name is the starting address of the pointer. You can't just set it off to some another address. Reason being, then that becomes that memory location is not being pointed by anything. So how do you put it? Reallocating that memory becomes difficult. As in, you're not something is not pointing to it, so it just becomes dangling. So that's a no-go. All right. Any questions so far? Okay. If not, then right. If not, then we'll take some more examples. Okay. As usual, include the IOStream header file to print outputs. We'll define a class this time. Okay. It can be, let's say, like have some public numbers. Just have integer I close to 7. Okay. Class B. Public. This time it will have double or in D goes to 7.5. Okay. Or 9.5. We'll have the main function. We'll define the objects now. So for the class A, the object name will be small a, small b of data type B, capital B. We can go even further. So define a pointer, okay, of data type A star. So as in, it's a custom or user defined data type with class A being the data type. Okay, so A pointer, we can define it, let's say P, which will be the address of A. Very similar. Q having the data type B and storing the address of B. Okay. Next, I'll write few sentences and you guys can take a try if this will are all these valid statements or they have some problems or which is it? I'll just describe a little bit. So I'm setting A equals to B. Okay. So one data type into another. Okay. Of one class to another. Another is here the same thing, but with the explicit cast. I'm explicitly casting B to A. Okay. And A small a is the object of data type capital A. Okay. Then do the opposite. All right. So this is another example. Other than that, we'll try to set now the pointers P equals to Q, the opposite P equals to P. Then, yeah, for now, maybe just this. So comment all these lines. This should be able to go. Yeah, so far so good. Right. So what I'm asking here is, if I comment these, if I uncomment these commented lines, what do you guys think will happen? As in, it will throw errors. It will throw basically it will be comparison errors, runtime errors. Is it allowed? Is it not allowed? No, yeah, this is defined, needs to be defined. I don't need to comment that. Okay. Yeah, I'll proceed one by one then. Okay. Yeah. Right. So I think this is fine. We're defining A and B, and here we're defining P and Q. Just the extra thing here with all the new notations might look a little confusing, but it's essentially, since we have defined A and B, okay, of certain data type, we can take their addresses and put it in new pointers. So that is absolutely fine. You can do that with inbuilt data types like integers, floats, doubles, and all. You can do that with even with custom data types. Okay. So which can be like A and B. So the class names, right? Sorry. Now, if we take this line, we're trying to set one class type, one object to another. So now essentially we're saying my variable A, which is of data type A, capital A, okay, is now storing small b, which is of data type B. So this is not allowed. Okay. So C++ prohibits this. You can't set class objects from one to another, at least implicitly here. What about explicitly? Okay, so this is also not allowed. Okay, so reason being, when you have an object, it has certain things associated with it. So like the public member variables and many other things, functions and so on and so forth. Overwriting the complete space of A, okay, by with B is not really, if you think about it, um, it's actually prone to errors. Okay, it might be taking some space and like it's like deallocating the whole thing and then overwriting the complete thing. Okay, you might actually overwrite only certain memory, maybe not the complete thing. Maybe you're asking for a more memory than it already had. Okay, so you can actually, if you think about it, you can sort of run into these issues. So this is also even not allowed. Same argument. It doesn't matter what you're converting from where. This is also not allowed. Okay. Similarly, from here, implicit or explicit, you can't change or overwrite object into another. Okay, even through explicit casting, even by implicit casting. All right. Then, what about pointers? So the answer here is also the same, and one cannot change it. Okay, same here. Now, the situation being that you cannot even, like, the same reason being you cannot change a existing object of certain data type into another, okay, or vice versa, like we see here. If the same case holds for the pointers also. If you try to change one pointer to another, okay, implicitly that is not allowed. Something similar we saw here, okay, trying to change pointers, right? Unless you actually explicitly cast it, okay, changing pointers implicitly is not allowed. Yeah, that's what we're doing. We're trying to change it implicitly. So now the next question is, what if we change it explicitly? So P is of I is is a pointer, so A star, then Q. Okay. Similarly, here will be P, B, Q. Okay. What about this case? Remember, we were able to typecast when we explicitly change the data type as a double pointer. Okay. Something similar by doing here itself. Here also. Okay. Any answers? Right. So thing is, here we can actually try to compile this and I'll just show you guys. Yeah. Yeah. So thing is, this one is fine, actually. Okay. Meaning, so remember P was defined to be a pointer, Q was defined to be B pointer. That will not change. That will always stay the same. So when you're trying to write something to P, whatever the other pointer is, you have to typecast it. So P has to be always typecasted, like whatever your variable is. So Q is something, right? So it's B pointer. So we'll typecast it to A. P was A pointer, so we'll typecast it to B so that this statement's hold. Now, what I'm trying to say here is as compilation goes, okay, so this won't produce any errors. As in this is allowed, okay, from compilation perspective, as just what we saw now, just now. But thing is, what does it even mean, right? So to think about it, pointer typecasting, okay? So you have some pointer, you typecast and you sort of, you typecast it, right? Implicitly, sorry, explicitly here and rewrite to some other pointer. This is shown to be allowed for both classes and inbuilt pointers. Okay. In case of inbuilt pointers, there is a mechanism. So now this is something you have to keep in mind. It's essentially saying I have a pointer which has an address. I'm pointing to some data type. Okay, some place. I know how to read that memory location of by either treating it as double or integer or treating it as is a class B pointer. So as in class B or class A. Okay, that's where it ends. Now there's an important distinction here. What happens after the conversion? How do you read it? Here, it at least means something. There is a rule for reading doubles. Doesn't matter what the sequence of integers are. Sorry, the sequence of bits are. Okay, it was an integer. Okay, now you're treating it as a double. So that same sequence of bits will be treated as floating point number. So there's a rule for that. What about uh, classes? Turns out it will just throw garbage. Okay, can try to print it as in. Let's try to print the member variables. Okay. So we'll use the arrow operations. Okay, so P is of A, P has I. Okay, so we'll have I. Will dereference as in access Q, its member D. So the same thing. But this time, let's have this commented and print this. So the value stored in I of the object P, okay. So as in the pointer object P is 7, and for D it is 9.5. That's what we have already. Now what happens when we write these things and then try to read. Okay, maybe just go one by one, line by line. Okay. So yeah, that's the thing. It tries to print something, but it prints zero. The reason being that it did overwrite it, okay, but you have to understand, just because we are saying treat this memory location that you hold, okay, as certain data type which you are defined to initialized. Initially, it makes sense, as in you're trying to access the value at A, okay, and accessing its members I as 7. So that is fine. That while trying to access with PI, that is okay. But now after it being overwritten, uh, there is a member which has Q. It is pointing to some address. Now we are treating that member as a different data type A. So what does it even mean or do, right? So hence we'll get, honestly, this is like undefined behavior. Okay. So you have to be careful while trying to explicitly cast pointers. With inbuilt data types, there is a rule for it, but with classes, it can actually be anything. Okay, so let's do that. Yeah, as you see, it tries to print something and then there'll be certain memory location. Okay, it will try to read off that value. And in the process, it printed this some number. Okay, we have both of them. Yeah. With Q, at least it printed the same thing. The reason being we overwrote Q and then again back. So yeah, that is fine. Okay. I hope you guys understand the difference. If I comment just this line and then print, if I comment this line and then print, and then if I comment both the lines, it print and then print. So there are differences between the runtime. All right. With compilation, both of them are allowed. And the reason being is just we're telling the compiler we have certain pointers, we want to treat them as different data types. That's it. Compiler allows that. It doesn't really ask what what is it even, does it even make sense to do it or not. Again, that depends on the developer or the writer of the code. Okay, any questions? Moving on to next example. Define the same uh, two classes as A and B. I have the main function, same data types defined. So two objects of A and B, then two pointers. Okay. Void pointer R. Okay, will have the same. I would say a very similar question. Setting A equal to B. B equal to A. Equal to Q. Equal to P. R equals to P. Okay. R equals to Q. P equals to R. Equals to R. Right. That's same earlier, like the first example we saw before. But in this context, we have custom data types also involved. So guesses. Yeah, can include return 0. So if I uncomment these lines, which one will throw error, or all of them will throw error, some of them will throw error? What do you guys think? Okay. So A equal to B will throw error, right? Equal to yes. Equal to Q and Q equal to P because that's the implicit casting of pointers. That's correct. R equal to P, R equal to Q is okay. That's correct because it's void pointer. And setting P equal to R and Q equal to R also will throw error because they're trying to cast void pointer implicitly. But if it's explicit, then that is okay. All right. Yeah, good. Correct answer. So moving on to the next example. So again, define the same two classes. Here, I'll just define it to be integer data A. Okay. Integer data B. Yeah, oh, okay. I'll mention the answer. So, oh, right. I made a miss. I did not put something I wanted to. Okay, your answer is correct, but I'll make a certain slight change. Okay. In this case, I'll make B a derived class of A. Okay. Now what do you guys think will happen? Okay, my bad. I wanted to actually give this example. I was thinking, why did I repeat same thing? Yeah, it's pretty much the same, but there's a slight difference. We'll come to this example later. We'll come to this example later, but let's do this one first. We have a base class, okay, A, which is public, has public member integer I. We make a derived class B, okay, from A, and then this is the derived class, okay. Similar, very same to similar to previous case A and B. We have defined small b objects, small p small q pointers to that objects. Okay. Then sorry, and then define the same lines. Okay. So what do you guys think will happen if I have this piece of code? Sorry, excuse me. So okay, I'll maybe try to give the answer. So the thing is, oh, okay. So A could be error, P could be Q. Okay. Uh-huh. Q equal to P error, R equal to P is okay, R equal to Q is okay. Error, error. Yeah, most of our answers are correct, except one, which is the first one actually. So the thing is, A equal to B will not throw an error. Okay. We can actually confirm that. So let's compile it and see. This here I just need the comparison errors. Okay. Yeah, that will not throw an error. Okay. So let's try to see why is that so. If you think about it, A is the base class, right? B is the derived class. So when you're trying to set objects like this, okay, the C++ standard actually allows it if you're trying to write a derived class object to a base class. Okay, so hence in this case, it will not throw any error. But if you try to write a base class to a derived class, that is not allowed. Okay, so this will throw an error. Now, P equal to Q, it's trying to write a pointer to another pointer. Okay, you can see. Yeah, that's fine. Okay, because it's definitely writing a point, another one pointer to another. But remember, in the hierarchy of things, okay, pointer, the uh, data type, A pointer and B pointer, one is actually a derived class of the other, and one is the base class. So again, it doesn't throw an error. Okay, the next one, Q equals to P. Let's see. This throws an error. Okay, so it can't assign B star. Okay, to from A star. All right. Void pointers as usual, not a problem. So no worries there. And these two, yeah, they'll throw error because implicit casting of void pointer is not allowed. Okay. So just comment this. All right, good to go. All right, just something to keep in mind. When you have derived classes, okay, then uh, overwriting objects or their corresponding pointers. Sorry, Ravi? Oh, yeah. Overwriting objects or their pointers, it's sort of allowed. Okay. What does it actually mean or not? That's a different thing altogether. But at least from compilation perspective, this is allowed. Okay. Something to keep in mind. Okay. Next. Okay. Define the main function. A, similar to before. Define the two objects. Okay. Then try to access data member A. Okay. Let's say store 3 in it. Okay. B, data member. And this time, let's make it a derived class. Okay. So now we can access the data member A of the object B also. Okay. Let's call it 10 and this call it 8. So A dot data, B dot data B, B dot data A, that's fine. Next, so after setting these values, define a pointer A. Okay. So I'll just write it as that define the variable as P. So it's easier to identify. B star pointer B with address of B. And let's see how P of A, data of A, P of A. So to access member variables through pointers of classes, you use the arrow operation. And then we'll do the same thing. Access data A. Okay. And then end the line. Very similarly, we'll do the same with P. Okay. Then access A of B. Okay. Yeah, let's see this output and then we'll move on. Okay. Essentially, what we did is we created the objects. Okay. Set the values, defined pointers. Okay. And then we're trying to print. Pretty much straightforward, right? Create 10. Okay. So that's what we defined them to be. We set the values. Those are public member variables. So the objects themselves, right? So the object themselves are accessible outside and we can set those values. Okay. Now P of A or P of PA or PB, they're just pointers. Okay. And once the value is set, they're actually accessing the same memory location of small a and small b. Okay. And we're accessing the same member variables using this arrow operation. Okay. And then the data A, data B, member variables are getting accessed. The values as printed is what we actually expect, okay? Because that's what we actually set them. Now remember, A itself, object A has data A, but not just has data B, but it has data A also, because it inherits the base class member variables also. Okay, remember that. So when we access data A for B, as like set it to 10, it will print 10. Okay. Then what if we set P of A? Okay, we set it as address of A before. What if we set it as address of B? So remember, here is the same situation that we saw last example, where we're trying to set an object of derived class to the base class. Okay, the object of base class to derived class. Similarly to the pointer also. The derived class pointer to the base class pointer. Okay. So this is allowed. Just try to compile and confirm. Yeah, that's fine. And we'll try to print the same thing again. Just have it done. Okay. Right. Now let's see what will be the output this time. Yeah. So, right. Now this time, the pointer A now points to B. Okay. All right. So when you try to access A, it now prints 10. Why? Because B, when it inherited data B and data A, okay, now you're trying to access data A of B actually. So which is 10. So it's not the data A which contained 3 before. It is now data A which contains 10. So that's what you gets printed now. Okay. And B is still the same. That did not change. So that still remains the same, 8 and 10. So those were the previous values. So that is fine. What if now you try to access A's member variable B? Okay. What do you guys think will happen? So remember, B had data B. Okay, so class B has data B, and we gave its address to pointer A. So now that pointer, will it have access to the data B? So that's what you're trying to print here. So a quick compilation will say you can't, because it was never declared there. Okay, so that's the reason you can. Why is it that the derived class can be used to typecast into base class? Because the extra members that derived classes have are just lost. Okay, the extra members are not present in the base class, but the members of the base class are always present in derived class. Okay, all right. So when you try to, so opposite would have been possible, like writing the base class equals to derived class. Sorry, derived class equals to base class. That means your base class should have access to the members on the left hand side, which is the derived class. That means you are defining something which is not present. Okay, so hence that is not allowed. All right, so this is not allowed. Okay, so this is the overall. Okay. Any questions so far? Okay. In that case, moving on. We'll write it this way. So till now we saw about typecasting, but in a C style way. Okay. I'll introduce another form of typecasting. So to ensure why the C++ way of doing the same thing is a little different. Okay. While the C way doesn't really distinguish between the nuances, but the C++ way actually does. So to appreciate that even more, so far it was just to all the typecasting we did, or the explicit typecasting we did, okay, was a C style way. So so that you guys understand the concept first. Now we will make a distinction between the each typecasting itself. So for that, let's first see about cost casting. Okay. Okay. So normally when you have a function, okay, take some parameters usually. Let's say it was take some const integer, absent reference. Okay, some constant reference have a variable, okay, and it has some body. That is fine. Here you can try to pass some variable I. Okay. So in the function call, you pass I, it will take that as a reference. Okay. And remember, the ref variable and I variable will be treated as the same thing. The difference, small difference being that in the scope of this function body, okay, in whatever the body it has, the reference variable cannot be changed. Okay, because it is a const. It's a const reference. Okay, now let's see some nuances between the differences. So take some more examples. Integer I equals to, let's say, 10. Integer pointer P equals I. Okay. Let me call it as PTR. Okay, as I itself. Okay. Now ref as mine. Okay. So as you can see, this is a perfectly valid code. You have I, which is which has 10 in it. Okay, it's an integer. It currently stores the value 10. We have a pointer PTR pointing to the address of I. So basically, dereferencing the pointer will point us to 10. We have a reference ref to I, So essentially, we can treat ref as the same variable as I, okay? And when we change reference to 9, I also changes. Okay. Next, we'll define um, the same thing, okay? But this time with constness. So let's define const integer pointer. Just call it const ptr with the address of I, okay? A const reference, integer reference. We call it const ref with just I, okay? Now what happens when you try to change this const reference variable to 9? Let's see. Yeah, that is not allowed. The reason being the const reference variable, which yes, it is the same as I, but the extra thing is that it is a const reference. So you're not allowed to change the variable from the reference itself. Okay, so this is not allowed. Hence error. Okay. So to that, what you can do is something called a const cast typecasting. What does that mean? So I do a const cast. Okay. So you pass in the template the data type that you are casting into. So that will be integer reference. Okay. And in the bracket, so remember this is a function. So use the now you have to give pass as a parameter. So the ref variable, hmm, what I mean is this const reference variable, not this ref variable. It is this one it can already change, so it really doesn't need to have a const casting. But you pass a const integer reference. So integer reference is the one you pass here, and it is a const data type. So as you pass it here, equals to 9. Let's say. Okay. Now let's say you change. Yeah, that's completely valid. Why is that so? So let's try to understand the difference. um, Initially you had a member variable I, okay? So now you were able to you stored some value to it. That's fine. Now you defined a pointer to it and a reference to it. So they can also change the values. So here, like you try to say ref equal to 9, it will change the value. If you try to say dereference ptr and store 9 there, it will also change the value at I. Okay, so that is good. Like so far so good. But if I have a const integer pointer, I, okay. So const integer pointer, you can't you can't do the same thing. Can't dereference it and store 9 to it. Or you can't just overwrite const reference like here to 9. So that is not allowed. Because these variables themselves have a data type to respect. So these are const data types. So they themselves cannot change a value. Okay, it is pointing to. Okay, so to temporarily allow them to change the value there at the original position, you do a const casting. I know it seems like you're casting it to be a const, but the interpretation is that you're temporarily casting it to be a non-const. Okay, I know it's a little weird to from the uh, function name. Okay, but remember, const casting does not mean it casts to a const. It means it takes a const reference, okay, here in this case, and casts it temporarily to a non-const so that you can change the value. Okay. Similarly, One can also do it this way. So here it was a little explicit, like just stored it this way. Can also do it in this way. So just cast to 9. This will be the C style way of writing the same thing. Yeah, that's allowed. So here we did the C++ way. Here's the C way. We're explicitly casting it temporarily to an integer reference and then overwriting it. Okay. Now let's say I try to dereference const pointer and then try to write 9 to it. Again, as I discussed before, this should throw an error, okay? Because still has to respect the fact that const pointer is a const. So it should not be able to change any values. Okay. So this will throw an error. All right. And what if we just typecast that to integer pointer? Okay. And then write 9 to it. Okay. So it's not sure what. So yeah, what if one does that? Again, that is also not allowed. Oh, sorry, my bad. Yeah, again, that is also not allowed. Okay. But you can achieve the same thing, okay, by doing a const cast for the pointer also. Okay. So first of all, you have to, it takes integer pointer, okay. Here it will be instead of the reference, it takes the const pointer, okay, and then you have to dereference it. Okay, it basically casts const pointer into an integer pointer, okay, and then store 9 into it. Okay. Just a second, is this correctly? Yeah. So you can do the same thing with the dereference. So you can typecast it into a integer pointer, okay, and then write it. So the previous syntax will throw error, but this one will not. Okay. I'll just mention it this way. But the C++ way is little more clear in this context. You're trying to dereference a const casted const pointer. Okay. So the const pointer was already const integer pointer. So when you pass const integer pointer to the template of const cast, okay, so it temporarily disables the constness, makes it an integer pointer, and then when you dereference it, you can store 9 to it. Okay. So this is the way to use const casting. And then finally, we can just print I in all the cases to see if it actually made the change. Okay. Yeah, that's 9. Okay. I do not have this also, it will be fine. Any other way? Yeah, the reference is also here, so it will be 9. But in this case, I think it should 10. Yeah. Okay. So this is the first thing we saw about how to do the typecasting, but in the C++ style, right? So that's where we will have, we'll use castness. All right. Okay. So you can do the same thing with the C style, but here the intention is not exactly clear because when you typecast one from the another, it just says what you're typecasting to. Okay. It doesn't say what it is actually doing in this case. Okay. So we'll see more examples of uh, typecasting. Okay, from from the perspective of C++ in the next class, where the intention of typecasting is made more clear, and as someone who looks at the code, okay, it's more readable also, and the intention is clear. And that is also a very important thing about coding practice. A very good coding practice, the intention should be clear. Okay, right. Yeah. If you guys have any questions, feel free to ask. We'll continue the next part of so next class we'll learn about some of that. Yeah, next class we'll learn about more about this const castness. Okay, we'll learn about reinterpret cast. We'll learn also about static casting. It's essentially all the forms we already have seen in previous uh, cases of typecasting, but now they'll be more formalized as to what each form of casting even means. Okay. All right. You guys can feel free to leave. If you guys have any questions, to ask, and I'll be happy to answer them. Furthermore, yeah, as I repeat every time, do practice questions. The more you practice, the better you get at it, get better you understand these concepts also. Okay. They can be a little tricky to grasp at first, but when you write the actual code and make changes, okay, try to then you better understand what each line actually is doing. Okay. So the top-down approach, as in starting from the first line, then the next, and then the next, and then the next. There is the order to which C or and even C++ follows. Okay, more or less most of the programs follow this. Okay, so going step by step and commenting and uncommenting, you can actually understand what each line is doing. Okay, all right. So with that, yeah, happy coding. Okay, if there are no questions, we can probably continue the next class. Okay, see you guys the next class.